So we're going to continue our review over quadratic functions. We looked at factoring quadratics, factoring completely, and solving by factoring. And today we're going to look at the process of completing the square. So just to remind you, there are three main forms of a quadratic function. There's standard form, factored form, and graphing form. And they each have their purposes, but today, for the purpose of completing the square, we're going to use that process to rewrite a quadratic function that's in standard form and change it into graphing form. Now you might be asking why this is important, and the main two reasons is that this form, graphing form, is especially helpful when you're trying to graph a quadratic function, but it's also used, completing the square is also used when you have a quadratic function that's not factorable and cannot be written in factored form. So we're going to look at one of these, and we're going to rewrite the function y equals x squared plus 8x plus 10 into vertex form. And I'm going to utilize algebra tiles to help me do this and visualize. So I have this equation, y equals x squared plus 8x plus 10. And the process is called complete the square because we're going to do just that. We're going to make a square. So I have 8 x's. I'm going to put half of them on one side of my square and the other half on the other side. And then I'm going to use my unit tiles to fill in my square. Now you might be noticing that my square is not complete. It has some units missing. So I need to ask myself, how many units do I need in order to complete the square? Well, I need 6 units. But in order to add those 6 units to complete the square, I need to make sure that I'm adding 6 to both sides because of the property of equality. Rewriting my equation as y plus 6 is equal to x squared plus 8x plus 16. I now have completed my square, and I can rewrite that square as a product of its length times its width. It has a length and width of x plus 4, so I can rewrite x squared plus 8x plus 16 as x plus 4 times x plus 4, or just x plus 4 squared. And finally, to rewrite it as a function, I need to isolate that y by subtracting 6 to both sides, leaving me with y equals x plus 4 squared minus 6, changing it from standard form into vertex form. Now let's look at this on a graph just so we can confirm. Here is my quadratic function in standard form, and then here it is in vertex form, and you'll notice that they are the exact same function, and I just want to note that the vertex is at -4, -6. We'll take a look at that later. So they are equivalent. Let's try another one. Rewrite the function y equals x squared plus 4x plus 10 in vertex form. Here it is on an equation mat. I'm going to build my square. I have 4 x's. Let's split them in half, 2 on one side, 2 on the other, and fill in my square. Well, what do you notice this time? Well, this time I have too many tiles. I have 6 units too many. So instead of adding tiles to both sides of my equation, I'm actually going to subtract, and I'm going to subtract those 6 units so that I only have 4 on the right side of my equation. So I have y minus 6 equals x squared plus 4x plus 4. Now that it's a square, I can rewrite it as a product of its length times its width, which is x plus 2 by x plus 2, or just x plus 2 squared. And finally, writing it as a function by adding 6 to both sides, y is equal to x plus 2 squared plus 6, changing it from standard form into vertex form. Again, let's just look at this one on a graph. We have x squared plus, oh, that was the last one, hold on. We have x squared plus 4x plus 10, and we have x plus 2 squared plus 6. Note that they're the same, and note that the vertex is at -2, 6. All right, so now that we've looked at those, let's see if we can find the pattern between why this might be called vertex form. So here are my vertices and their corresponding functions. And I want to look at the form for graphing, the graphing form for a quadratic function. And I want us to look and see if we can see the pattern of where we can visualize the vertex in our equation and why this might be beneficial. Do you see the pattern? Well, right here in this equation, this reads as the opposite of h and then k. And if you look in the vertices of each of these, the opposite of h is represented inside the parentheses with the x, and the y coordinate is represented with the k on the outside of the parentheses. So h is inside the opposite of h, and then k. So this pattern is true for all of our functions written in vertex form, and again, it's beneficial when we're trying to graph these. So I want to do one more without algebra tiles, and we're going to see if we can identify the vertex following that pattern. So rewrite the function in vertex form. Now, algebra tiles are great, but we're not always going to have them. So I want to show you how to do this with a generic rectangle. So if I were to build this square on the right side using the tiles that I have an x squared, and I have negative 6 x's. And when we were building those squares, I had to take those x's, those my b term, and I had to put half of them on one side of the square and the other half on the other side. And if I split negative 6x in half, I have negative 3x and negative 3x. Now, in order to figure out how many units I need to complete my square, I need to think back to when we looked at the diagonals of generic rectangles, and we learned that the product of each diagonal is the same. So when I multiply negative 3x times negative 3x and I get 9x squared, that's going to be the same product if I multiplied the other diagonal. So I need to think to myself, what times x squared is also going to give me 9x squared? And that's 9. So I need 9 units to complete my square. Well, right now I have negative 1. So in order to make it a positive 9 units, I'm going to have to add 10 units to both sides of my equation, rewriting it as y plus 10 equals x squared minus 6x plus 9. I then can find the factors of each of the partial areas and rewrite my area as a product of its length times its width, which is x minus 3 times x minus 3, or x minus 3 squared. And finally, subtracting the 10 to both sides to rewrite it as y equals x minus 3 squared minus 10. So here's the standard form and the vertex form. And I have one final question. What is the vertex of this quadratic function? Now that we learned a little bit more about vertex form, what coordinate would the vertex be at? It's going to be at positive 3, negative 10. Again, the x coordinate represented by the opposite of h, and then the y coordinate represented by k. So positive 3 and negative 10. So there's just a review over how to complete the square using algebra tiles and a generic rectangle.